Hi, this is Brian Fogarty, and this is a video for Chapter 12 of the book Quantitative Social Science Data with R, second edition. So this is the first video of this chapter. This chapter is all about OLS, linear regression assumptions, and diagnostics, and potential solutions to violations of the assumptions. Okay, so this is the first video of this chapter. So I just to point out I have a new R Markdown file. I'm going to I saved it, but I'm going to set the library and also the working directory. Okay, and then we are going to in this video just look at functional form. The other videos looks at different assumptions and diagnostic testing and solutions. So we are going to use the model, the regression model we had from Chapter 11, which uses data from the 2020 Scottish Index of Multiple Deprivation. And that linear regression model had percent depress as our outcome variable, and then we had employment deprived, overcrowded, and urban as our predictors. Okay, so what we're going to do is just highlight all of this and run it. Okay, so this is the results from last time in the previous chapter that we looked at and talked about. So again, we're going to look at functional form. We're going to use this package called lindia, which is like India with an L, or Linda with an I before the last A. There's a whole bunch of different packages out there that we could use. I've just been using this one recently. I kind of like it because it's pretty simple and straightforward to use. So we're going to use this package, and we're using this function gg underscore res fitted. So what this does is that it gives us a plot of the residual versus fitted values. So we just do ggplot res fitted, and then the model 1 plus, we don't have to, but we're going to include a theme, a ggplot theme, just so it's easier to see the results. And we're going to use theme underscore bw for black and white. All right, so I'm going to highlight this and run this. Sorry, it was in the window here already. All right, let's make this a little bit bigger. Drag it. Okay, so we have our fitted values on the x-axis, and our residuals are on the y. What we're doing here is we are looking to see at, as we increase on our fitted values, are the local means of the residuals roughly 0? So we're eyeballing this, essentially. So we see, like, through the middle here, you could be like, yeah, pretty much. But then once we get out here, we see that the residuals really are below 0. So it's not likely that their local means are 0. So based on that, we probably have violated functional form. We care about functional form because it's an assumption made that we have the correct functional form as part of the Gauss-Markov theorem. It's one of the more important assumptions made with OLS linear regression. Probably heteroscedasticity is, I'd say, probably the most important. But we should care about this and try to fix it if possible. Okay, so different people have different preferences about how to do diagnostic testing. Some people just prefer to look at visualizations and leave it at that. I don't always trust my eyes. So what we are going to also do is look at a formal test for functional form. And we are going to use the lmtest package. So we're going to load that. And the test we're going to use is the Ramsey reset test. So the function for that is reset test, okay, and then open parenthesis, and then model 1, and then power equals 2:3, and then type equals fitted. So what this test is doing is that it includes, here is very, very common, it's kind of a standard way of doing it. It includes squared and cubed versions of the fitted values of y as predictors. So it includes them as predictors, and then it compares, it looks at how well our model does at explaining the variance, the original model, model 1, to this new version that has the squared and cubed predictors. Again, the squared and cubed fitted values, the y-hats, as predictors. And so if there's not that much gain by including the squared and cubed, then we'll find the test say like there's not, there isn't a benefit from it. If there is a big difference, the test will tell us that we should look at the functional form of our predictors to see if there's a problem with them, if we have them specified correctly. All right, so let's run this and take a look. Okay, so we have all these results here, stuff down here. We really just practically are interested in this here. We're looking to see whether it's 0.05 or smaller. So the null is that there's not a significant difference between here model 1, our original model, and then this version where we have the fitted squared and cubed versions of y-hat. So this is below 0.05, so we reject the null, and this other version is better. So what that says is that we have violated functional form, and we should see if we can fix this problem. We're going to see here that there's a lot of these assumptions, we often violate them. There are ways to correct them, but then correcting them doesn't, leads us to do sort of non-intuitive things. So sometimes we just say, yeah, there's a problem, we're going to punt on it and just not worry about it. All right, so what we'll do to check this, to see, right, what predictors might there be problems with, we are going to use a plot called a component plus residual plot. So we're going to get this from the car library. All right. So we load the car. Just note, the car package also includes a recode function. So if we were doing recode with dplyr or forcats, that will conflict. So we might need to detach it if we're doing this whole thing all together. All right, so the function is crPlots, and then model 1. Okay, so let's run this and take a look. All right, we're going to zoom, and then I'm going to drag it to make it bigger. Okay, so don't worry about this down here just because we can't transform a dummy variable, an indicated variable. So again, the idea is if we violate functional form, we should do something that corrects it, and by correcting it means transform it in some way. So if we look at these plots, the blue dashed line is what it should be, okay, and this sort of purple pink is what it actually is. And when I say should be, right, this is what a linear relationship should look like. This is what it actually is. We see there's this curve here. Same thing. So that's with percent employment deprived. With percent overcrowded, again, here's the blue line, and we see here that this is what it actually is. All right, so it seems like both of these, there's potential problems. Okay, so there's potential problems with those two variables. let's use a test as another way to see whether or not we're actually picking it up correctly, that those are the ones, and what we might be able to do to fix it. So we're going to use something known as the boxTidwell test. So it provides information, again, about whether or not the predictors that we see do actually have a problem and suggest the solution. So one thing about the boxTidwell test and the function that we're going to use is that we can't have zeros. And so I believe, let's look. I believe that both those variables have zeros. I'm just going to do a real quick summary, SIMD, and then percent employment deprived. Let's take a look. Yeah, there's a 0, and then it's going to steal this. Just check it for percent overcrowded. I'm pretty sure there's 0 too, or as well. Yeah. Okay, so they both have 0. So what we're going to do is we're going to add a 1. It's not going to change things really. It just adds a 1 so that it's not 0. Okay, so the function is boxTidwell, and then there's different ways we can actually specify this. We're gonna do it in this specific way. We're gonna do percent underscore depress, and then tilde. I'm gonna put a space there so it's clearer. Tilde, and then we're going to use the I function, which we talked about in a previous chapter. So the I function allows us to make a variable transformation on the fly, so without needing to create a new variable. Since we're not interested in the new versions of percent employment deprived and percent overcrowded that has the +1, this is a perfect place to use the I function. So we're going to do I, then open parenthesis, percent employment deprived, and then +1, right? And then plus, I'm just going to go down the next line here. The I function again, and then percent overcrowded +1. Okay, then we're going to do comma tilde urban FCT. So what this part is this is where we're excluding variables. So we're saying like ignore this. This isn't part of it. And we're going to do data equals SIMD. Okay, so that looks good. Let's run that. Okay, so we get a bunch of information down here. There's a couple things to focus on. First is this PR here. We're looking to see whether or not, well, there's also the stars, but we're looking to see whether this is 0.05 or smaller for both of these. If it is, then it says this is the incorrect functional form. We need to do a transformation. So that's the case for both of these. All right, so the plots that we looked at before suggested that. And then this is the suggested transformation. So what this means is it says raise percent employment deprived to 0.39, and then raise percent overcrowded to 2.03. So the percent overcrowded, 2.03, essentially it's squared. All right, so that's pretty simple to get our heads around. 0.39 is kind of weird, right? It's kind of a weird value. So I have more in the chapter on this. What we're going to do is rerun our model that we had. So we're going to rerun model 1. Okay, we're going to do it like this. So summary, we're going to do model 1. We're going to call it model 1A. That's what we're going to save the object as. We're going to do lm percent underscore depress, and then tilde, All right, then we're going to do percent employment deprived plus, I know this is kind of like, oh my gosh, percent, sorry, the I function, so this is where the transformation is coming in. Employment deprived raised to, we're going to use that caret 0.394. All right, so outside of that, plus percent overcrowded, and then plus the I function, percent underscore overcrowded, raised to 2. Okay, sorry, I'm just being careful, a lot of stuff going on here. Plus urban underscore FCT. I think that's looks good. Right, and then comma, I feel like I'm doing something wrong here. Data equals SIMD. All right, so let's hope that works. Okay, so it did run. All right, so that's good. Okay, so we get these results. What do they mean? Well, let's do this. Before we look at what they mean, let's rerun the component plus residual here and see if the linearity is fixed. So model 1A. Take a second. It's going to take a second. Okay, so let's click on that. I feel like each time that it gets smaller and smaller. I got to drag it more and more. It like doesn't. I'm sure there's something. There is some reason. Okay, so now if we look at these, we see that both of these, the effects appear linear, or more linear than they are, right? So the pink purplish line is lining up with the dotted blue line. Okay, so again, I talk more in the chapter about this, but I say, again, squaring something, that makes sense. There's ways to interpret it, but raising this to this value is just weird. It's just a weird thing. So sometimes people just say like, okay, you know what, like there might be a problem here. I need to assess whether I find, whether differences are the statistical significant differences of my predictors, are they different, and just live with it. I do discuss in the chapter ways that we can try to get a handle on predicting the effects of the transformed ones. Again, so I'm gonna leave it there. This is completely not satisfying, but these are the steps for testing, functional form, trying to do a correction, implementing the correction, checking it again, and then deciding what to do next, which often might just be like, I don't know. Okay, I guess all right. Let me step back. I guess, if we can make the transformation and we have a way to discuss the results, as I do in the chapter, then we should do it. We should make that transformation. All right, so that's it for this video. Thanks for watching, and I'll see you next time.